Whether you're, running for a bus or watching an elite athlete leap for a gold medal, motion is, well, it's everywhere. But what does physics actually tell us about how it all works? Okay, in this explainer, we're going to dive right in and break down the science behind every single step, jump, and journey we take.
So, take a look at this long jumper. Her goal seems pretty straightforward, right? Just jump as far as she can. But for a physicist, her motion is this really fascinating puzzle. And to even begin to solve it, we have to ask a super basic question. What does it really mean to move?
All right, to figure that out, let's go on a little journey of our own. We're going to start with the most obvious way we all think about movement, just plain old distance.
So, let's imagine you start at home and you walk to school. We'll say it's a nice, straight path, and the total length you travel is 500 meters. Super simple, right? Well, that length of the path you walked, that's what physics calls distance.
Okay, but the day's not over. Let's keep going. Now, from the school, you walk another 700 meters to get to the library. So you've got these two separate legs of your journey, one right after the other.
So, what's the total distance you've walked so far? Well, it's pretty easy. You just add the two parts together. You've got your 500 meters plus the 700 meters, and that gives us a grand total of 1,200 meters. That's the entire length of the path you covered.
Now, in the world of physics, a measurement like this, one that just gives you a number, has a special name. It's called a scalar. A scalar quantity just tells you about the magnitude, the size, the how much of something. In our little walk, that's the 1,200 meters. It's just a number, no other clues, no other information. But hang on, is knowing how much really enough information? I mean, if you were trying to give someone directions, just telling them a number probably wouldn't cut it, would it? This is where we need to add another, really important layer to how we think about this.
Seriously, think about it. If your friend is at your house and you just tell them, hey, walk 1,200 meters, where would they end up? Who knows? They could end up anywhere. They might walk in a big circle or go completely the wrong way. Clearly, the distance alone, it's not enough. So what's the missing piece? It's direction. You need a direction. Telling your friend to walk, say, 500 meters to the east, now that's helpful. Now they actually have a specific path they can follow.
And that little addition brings us to our next big idea, and it's a really important one: the vector. A vector is way more powerful than a scalar because it includes both magnitude and direction. It answers both questions, how much and which way.
So when we combine that magnitude and that direction from a specific starting point, like your home, we're doing something more than just tracking movement. We're actually defining an object's position. See, position is a vector. It pinpoints an exact location. So for our journey, the library's final position is 1,200 meters east of where you started.
Okay, so now we get it. We know the winding path we took, and we know our final position. But what if we wanted to know the most direct measurement? What's the shortest path between where we started and where we ended up?
Right, we went on this whole journey, from home over to the school, then to the library. But just for a second, forget that winding path. What if we could just draw a perfectly straight arrow, right from our front door to the library entrance? What is that line telling us?
That straight line, that shortcut, that's what physicists call displacement. It's the total overall change in your position from your starting point to your final point. You've probably heard the phrase, as the crow flies. Well, that's exactly what displacement is.
So let's put it all together. Here's the key difference, right here. The distance you walked was 1,200 meters. That's a scalar. It's the total ground you covered. But your displacement was 1,200 meters times east. That's a vector, your direct change in position from start to finish. Now, you might be thinking, wait, the number's the same. And in this particular case, you're right. But that's not always how it works, not by a long shot.
So let's really see how different distance and displacement can be. We're going to put everything we've learned to the test with a new problem, one where the path is definitely not a straight line.
All right, picture this. A dog is playing fetch. He gets super excited, runs 80 meters to the west to grab a ball. Then he turns right around and runs 27 meters back to the east towards his owner. Now the total distance the dog ran, that's the easy part, right? It's just 80 plus 27, so 107 meters. But what's his displacement? Okay, to figure out the displacement, we have to add those two vectors together. But wait a minute, they're in opposite directions. How do we do that? Well, there's a neat trick. We just decide that one direction is positive and the opposite direction is negative. So let's just say west is positive. That means the 27 meters east becomes negative 27 meters west. Now they're speaking the same language, and we can just add them up. And what do we get? The dog's total displacement is only 53 meters to the west. Isn't that wild? I mean, the dog ran over 100 meters, but it only actually ended up 53 meters from where it started. That's the power of understanding displacement.
So, what does this all mean? Let's bring it all the way back to that long jumper we saw at the beginning. Why does any of this actually matter in the real world?
Well, think about it. The long jumper isn't actually trying to maximize the distance they travel. I mean, that would include the whole up and down arc of their jump. No, their real goal, the thing that wins the gold medal, is to maximize their horizontal displacement. It's all about that straight line change in position from the takeoff board to where they land in the sand.
Okay, let's wrap this up with the key points. At its very core, motion is simply a change in position. We can measure the entire path we take using distance. That's our scalar, the one that only cares about how much. But if we want to know where we actually ended up relative to where we started, we need displacement. That's our vector, the one that tells us how much and which way. It's really the ultimate measurement of how far you are from your starting point.
And that leaves me with one last question for you. Think about your own route to work or to school or wherever you go. With all the twists and turns you take, what's the total distance you travel every day? And then, what's your total displacement? The difference between those two numbers? Well, it just might surprise you.